Hello everyone. In this video we are going to discuss about depth first search. In the previous two videos we have been seeing two uninformed search algorithms. One is breadth first search and the other is uniform cause search. One of the limitation in both those approaches is that there is a huge consumption in memory. The number of nodes which need to be stored is order of b power d. So depth first search can overcome these memory requirements, but at the cost of some other parameters. So let us see how depth first search will help us in overcoming the limitations which we have seen in breadth first search. So depth first search always expands the deepest node in the current frontier of the search tree. So it pursues only one path. It goes deeper and deeper until it reaches to the leaf node. So DFS, the implementation involves LIFO data structure, which means last in first out, which can also be called as stack. So in a LIFO queue, we always pop the recent node and we try to expand the particular node. Whereas in breadth first search, we were trying to do FIFO, which is first in first out. Whereas in depth first search, we are trying to pop the last item which has been sent into the frontier. So generally, we have seen breadth first search and the uniform cause search in a graph way of implementation, where we have generated the child nodes and we were testing for the goal node, and we were trying to reach to the target goal node. Whereas in DFS, we follow a recursive approach where we call the same function once again and try to reach until the leaf node. So, but although the DFS has the advantage of giving us the less memory, DFS is not complete, which means that it does not guarantee that it will reach to the goal node. And it is also not optimal, which means that there is always a chance that DFS will end up in a solution which is not of a minimum cost and not the optimal one. The time complexity in worst case is order of b power m, where b is the branching factor and m is the depth. Which means that in the worst case, if the node is the last node, you have to pass through all the nodes before you reach to the goal node. And so coming to the space complexity, this is where DFS has the advantage because it doesn't need to save the nodes of a particular path once it has reached until the leaf node. If we followed a particular path, gone deeper and deeper, and came to know that there is no goal node in that particular path, we can ignore that particular path and we don't need to store anymore in the frontier or the expanded nodes, and thereby we will have a lot of reduction in the memory requirement. So the total memory required will be of order bm, big O of b into m, where b is the branching factor and m is the maximum depth. And because of this reason, it has been used very much in many AI applications like constraint satisfaction problem, proportional satisfiability, and logic programming. And we can further reduce the memory requirement from order of bm to order of b if we follow a technique called as backtracking, where in backtracking, instead of generating all the branch nodes, we generate only one successor and we pursue the path until it reaches to the leaf node or the goal node. So thereby we can have a complexity of order of m, which is just the order of depth of that particular tree, because we are not expanding all the other branch nodes. So this is one of the demonstration of how depth first search works. So as you can see, first it covers one complete path until it reaches to the leaf node, and then it goes back to the second child of the root node and it pursues once again the same way. Suppose if you have a graph which is cyclic, the DFS follows a different approach. For example, in this case, we can see the node A, it generates node B, and we immediately pursue node D. So the D does not have any children, so it goes to the second child of B, which is F, and then it goes to the second child, the child of F, which is E. And as we can see, we don't pursue cyclic paths in graphs, so we don't once again go back to A. So we then go back to C and G. That's how we reach to this path A, B, D, F, E, C, G. If at all, if we don't remember the previously occurring states, we will be having a cyclic path and we will not be able to come out. So that's how, this is what generates, so a periodic pattern we see when we repeat a cycle. So this is the time complexity of DFS. As we have seen just now, it is not optimal, or DFS is not complete when it is infinite state space. So which means that if the path is infinite, we are guaranteed to pursue only one path until the infinite, and if there is a solution just beside the first child, which is, suppose that if it is in a second child of the root node, then it keep on pursuing the first child's deeper and deeper nodes, and it reaches to the infinite without actually reaching to the goal node. So DFS is not complete in whenever it is in the infinite state space. So let's get back once again. So it is, DFS is not complete. DFS is not complete in infinite spaces. DFS is not optimal, and but the advantage is the memory requirement is way lesser, which is order of Bm, and the time complexity in worst case would be order of B power m. So this is about depth first search. Now let us see one more algorithm which overcomes the limitation of the depth first search under infinite state space. So that is called as depth limited search. So depth limited search, DLS, will have a fixed limit value where we pursue the descendants of a particular child only until a particular limit L. Once it crosses that particular limit L, we'll go back to the adjacent child of the root node and we pursue once again until the next limit, until the same limit L. So in this way, depth first search or depth limited search overcomes the problem of the depth first search in the infinite spaces. So even if we have infinite spaces, since we have set a limit L, so it pursues only until that particular limit L and it goes back to its adjacent nodes. So there are two cases. Suppose if there is a tree which has a depth D, and if the limit if we set L as which is less than D, then there is always a possibility that our goal node lies beyond L and we don't reach to that goal node. So so it becomes incomplete, and therefore it is not complete because there is a possibility that we will not reach to the goal node because limit L is under the condition that L is less than D. If L is greater than D, it is once again non-optimal because it pursues the whole path and there might be an adjacent node which is smaller. So the time complexity is once again order of B power L, which is similar to B power m or B power m, which we saw in DFS. So when L is m, it is nearly same, whereas space complexity is order of BL. So where B is the branching factor and L is the limit of the depth limited search. When L is equal to infinite, depth limited search becomes depth first search. So this is the pseudo code of depth limited search. So there are three states. One is cutoff, failure and success. So let's see each of these state when we will encounter these states. So consider this. So as you can see here, so there is three states. One is if you have reached the goal state, goal node, then we will reach to the solution. If we have reached, if the limit, if we reach to the maximum limit, we will call it as cutoff. And if the solution, if the goal node is not present in the whole tree, we will reach to a state called as failure. So these are the three states it reaches. And most important thing, both depth first search and depth limited search are implemented using recursive algorithm. So the recursive DLS, the function, is being repeated once again here with a limit, reduced limit. So each time it calls the same function once again with a limit reduced by 1. So it reaches to a point where either it reaches to a solution or a goal node, or it will reach to a point where the limit becomes 0, and therefore we call it as cutoff. So if any of these states does not occur and passes through all the nodes, then we will reach to a state where we did not identify, where we did not have cutoff, and therefore it becomes failure. So we will have either of these three states. So let us see with one example to get more clarity as to how this works. So let us take this tree. As you can see here, the node A is the initial node and node H is the goal node. So if the limit L is 1, which means that we are not supposed to traverse the nodes which are above the depth L is equal to 1. So under such conditions, we will have a traversal as A, B, C, D. And since we reached to the limit L is equal to 0, so since we reach to the maximum limit, our result would be cutoff. What happens if limit L is 3? So our goal node is within the tree, within the limit, so it will have a success. So it will, one or other way, it will reach to the goal node. So the traversal would be, it starts from A, B, E and I, F, J, K. It does not go to O and P because there is a limit L is equal to 3. So after K it goes back to C, G, L and D and H. That's how it concludes. And what happens if goal node is not there? And if goal node is not there, then it will traverse the whole tree, and it will neither reach the limit value as 0, nor it will have a successful outcome or successful reaching of goal node. Therefore, these when none of these two option happens, we reach to a state called as failure. So these are the three states which depth limited search has. So once again, the time complexity is order of B power L, space complexity is order of BL, and both it is not optimal and it is not complete. It has solved only one problem, which is to stop pursuing an infinite path. Whenever there is an infinite state space, you can limit the algorithm until a particular depth, and it will go back to the next adjacent node and it pursue the children of that. So in this way, depth limited search although solves one of the problem, but it has the same time complexity and nearly same space complexity as depth first search, and both the algorithms are not optimal and not complete algorithms. In the next video, we will be seeing iterative deepening and bidirectional algorithms.